So today we're going to look at some definitions of key terms for the graphs of polynomials. There are quite a few, so I would make sure that you're pausing and writing things down as I go. I'm just going to try to get through all the definitions before I then look at some organizational tips for you, as well as some additional things that can happen with graphs. So the first definition is an increasing interval, and basically what it says is as x increases, f of x increases. Algebraically speaking, it means that if the first value is less than the second value, then the output created by that first value will always be less than the will be less than the output value by the second value. So let's take a look at what that's saying. A lot of students, they read that and they have a little trouble understanding what it's saying. But here's a clearly increasing function, right? So this is clearly going up the whole time. So what it's saying is if I have an x1 here and an x2 here, that x1 is always less than x2, simply meaning that the x values are going upward. So what does f of x1 mean? It means the corresponding output value, f of x1, will always be less than the corresponding output value f of x2, because f of x2 would have to be larger in order for it to increase. So it's saying, basically it's saying as x goes up, y goes up, okay? So how do you find it? You simply examine the graph and determine the domain, it's answered as a domain, of the intervals where the graph tends upward. Now, the other idea here is something called a decreasing interval, which is exactly what you expect. It says as x increases, then the output values will decrease. And so, a visualization of that, same idea, but going downward. If I have a function that's clearly decreasing, like this function, and it's tending downward, then x1 will always be less than x2 because you read the domain of a graph from left to right. But in this case, f of x1 is actually larger than f of x2 because f of x2 is smaller because the graph is going downward, meaning the trend of the graph. And the way you find it mathematically is you simply state the domain in which this is happening. Okay, and the next thing that's really important is relative and local minimums and maximums. So a relative or local, these are synonyms. A relative or local minimum is simply a point where the graph changes from an decreasing to an increasing interval. So let's say a graph is going downward and then all of a sudden it goes upward. This is where a local or relative minimum is right there. How do you find it? You simply look at the point where the graph changes from increasing to decreasing. You can see clearly here the graph is decreasing here, but then increasing here. All right, the absolute or global minimum would be the smallest of these that you see. So let's say you had several of them, right? Let's say you had a graph, okay, like this. Then this would be the global minimum. But keep in mind that if the graph actually stops here, this is also a minimum, and that would be the global. The smallest output value on the graph is the global minimum value. So for relative maximums, it's the exact reverse. It's where a function changes from an increasing interval to a decreasing interval. So you can clearly see here that the graph is tending upwards and then stops and then starts tending downward here, giving you the maximum here. And a global maximum is the exact same thing, but in reverse concept as the minimum. So if a graph that does this, this one would be the global, but if it then goes up like this, this could be the global maximum too. Endpoints can be globals and they can be locals. So keep in mind that this would be a local and a global. This is the obvious local minimum, obvious local maximum. This would be a local and a global as well. An x-intercept is simply a place where the graph touches the x-axis. Many can exist in a function. You can have many of them. It is written as a point, whatever that value is, comma 0. And the way you find it is to substitute y equals 0 to a function and solve. You've done this many times. Like the last time you saw this, if you have a quadratic and you have something like this, right? The way you would find the x-intercepts of this quadratic is you would set the problem equal to 0 and solve. In this chapter, by the way, a quadratic is a type of polynomial, but in this unit, we're going to go to higher exponents than the square. The y-intercept is a point where the graph crosses or touches the y-axis in a function that only one can exist, you do this by plugging 0 in. So a lot of times it's called f of 0. Using this example here, you would have 0 squared minus 0 minus 12. So that one would be 0 comma 12. Again, every function has a y-intercept, but not every function has an x-intercept, or they could have more than one. So you could have one, none, or many. You do this by substituting y equals 0 in, or f of x equals 0. This one you complete and figure out by plugging 0 in for x. So to go to a couple more, here's a new one called an even function. Even means a function is even when it's symmetric to the y-axis, meaning it has a line of symmetry of x equals 0. So algebraically, you find that by plugging a negative in, and basically the negative will be canceled out by all the evenness of the graph, and you get f of x back out. An example of that, a very obvious even function, is the quadratic. So let's say I have f of x is equal to x squared minus 2x plus 3. That is not going to be even, though, because it will only cancel out here. So let me show you what I mean. If I put in negative x squared, so the exponent does not mean it's even. You have to actually look at this happening and see if the function will basically return the original function by plugging in a negative x value. So f of negative x is going to come out to x squared positive now, because a negative times a negative is a positive, minus 2x plus 3. But that negative there, because we have to plug a negative x into both, would make that a positive. So these don't match. So that's actually a neither. In order for this to be even, we would have to have a quadratic like this that doesn't have a middle term, because that middle term is going to cause issues with that elimination of that term. So if you remember what happens when we eliminate the middle term, and I'll show you a picture of this. So as you can see here, by eliminating the middle term, when I put a negative x in, I got the same function back. That's what you want. So graphically, the difference there, and this is important to understand, is that the first problem was some kind of parabola over here or over there. But this one, if you remember, the vertex of this parabola was 0, 3. So if you look at where this graph would be, it would just be up here 0, 3, and it would be perfectly symmetric to the y-axis. Another example of this, which we have seen, is if we had an absolute value graph on the y-axis. Notice the symmetry to the line y equals x has a line of symmetry at x equals 0. For oddness, oddness is very similar to this, but what happens here, it's a little bit more involved. So if I put a negative x into something that's odd, remember the entire thing would have to obey this rule. So if I put negative x into, obviously it wouldn't work with an even exponent. Again, it's not the exponent, it's the algebra, and for us, really, it's about the graph. So over here, if I had something like this, x cubed plus x minus 3, what's going to happen? I'll make it plus 3. I'll make it a little bit more obvious. If I put a negative in here, it's interesting what happens is I put the negative into this graph. In the first two will, in fact, become negative f of x, meaning opposite of the original. But the problem I have is that 3 isn't going to change over. So it doesn't change, right? So I have this happening where I get negative x cubed, and that's what this is saying. You need to be able to have a negative in front of your terms. This will change. Sorry, I wrote that down wrong. That's an addition. So it'll become minus. So you have that negative x. But the problem is the 3 doesn't. So in order for this to be odd, you would have to lose that 3. And now you can see that every term changed signs. And so what does that look like in a graph? And this is what really matters. If you're really concerned, like, well, there's a lot of algebra going on there. What really matters is you have a symmetric to the origin, right? So in this graph, if I had a graph that went like this and then had a perfectly symmetrical to that, that's an example of oddness. Symmetric at the origin, the point 0, 0. It's point symmetry as opposed to this, which is line symmetry. Okay, so just keep that in mind. Even for, is symmetry to the y-axis, odd is symmetry to the point 0, 0. Though many graphs are symmetric, only graphs that are symmetric and meet these characteristics are called even or odd. So you can have symmetric graphs, right? So you could have a graph that's perfectly symmetric, a perfect circle. But is this graph symmetric to the y-axis or the origin? No, it's symmetric to this point over here, which is irrelevant. They have to be symmetric to either the origin odd or the line x equals 0, the y-axis. There's something else called end behavior, which has a lot to do with domain and range, and you see it quite often like this on an assessment. And I put up here a translation of it. So end behavior is the comparison of the domain of a function with corresponding range elements. And so what that's saying is that x is going to go to the left side of the domain, and then you're going to tell me which part of the range that it's corresponding to. And then we're going to talk about x going to the right side of the domain, and then talk about its corresponding range elements. So let's take a look at a couple examples. The best way to understand end behavior is to see it, because you've already done it with domain and range, and it's just a new way of writing it. So if you ever see a computer-generated graph like this, please ask your teacher if there are arrows here. It's actually hard to get a computer to do that many times, so just keep that in mind. All right, so if we look at the domain of this from before, it would start at the left, beep, the whole time. So we have the domain goes from negative infinity to infinity, little review, and the range starts at the bottom here, right? So as we talked about before, we're going to label these axes because we see infinities in a lot of places. So if we start at the bottom, we would start right here and beep at -4, beep to infinity. So that would be 4 to infinity. So a little review from before, but now what's going to happen is we're going to splice this up basically. And what happens is this infinity is the left side of the domain. And so the question is, which of these range elements corresponds to the left side of the domain? And you don't have to use both of them. You might use one of them twice or one of them no times. So on the left side of the domain over here, the range is going to infinity. So you say on the left side, negative infinity, the range is going to infinity. And on the right side, which is this piece, right? So this piece right here is going to infinity, the right side of the domain. So over on the right side of the domain, what is the range doing? It's also going to infinity. And then students will immediately ask me, well, what about the 4? The 4 is the middle behavior. Notice the name, end behavior. Yes, 4 is important in the range, but it doesn't tell you what's happening at the ends of the graph, the extremes. I've actually seen this called extreme behavior, but in Virginia we call it end behavior. Let's take a look at one more in which we will be using the range a little bit. So I just gave you guys a line here. And if you notice, again, don't have arrows. So we're going to put arrows on the graph. It helps to label my axes. So here we go. All right. And so what I'm going to put in here is the domain beep the whole time, negative infinity to infinity. The range is just one number. It's just, watch, beep, beep. It's just 3. So if we take a look at this example, on the left side, the graph is going to negative infinity, but what is it doing? It's going to 3. And on the right side, the graph is going to infinity, but what is the range doing? It's also going to 3. So try not to get bogged down about using the range every time. Try not to get bogged down about using each piece of the range. It's saying, look only here. I don't care about the middle. Just look at the arrows and tell me what the arrows are doing in terms of the domain and range.